Yeah, I'll try to put most of the questions on the blackboard, but maybe not write the complete question. Let's just start. And if you have any questions, please interrupt. So for the first one, we get some matrix A. Okay, the first question is to determine the rank of A. Okay, so you need to know what the rank of a matrix is. I think the first definition is the dimension of the span of the columns of A. So if you look at the span of these 5 columns, then you will get some kind of vector space, and the dimension of that is the rank of A. And the easy way to find that is to reduce A. Right? So for very many applications, you need to reduce the matrix to reduced row echelon form, and then you can kind of just read the answer. So let's start with doing that. So I hope you remember what row operations you can do. Right? You can swap 2 rows. You can multiply a row with a constant, or you can add a multiple of 1 row to another. So let's see. The first step was to make zeros here, right? In the first column beneath this one. So we'll keep the first row. Double check if I have the right one. Okay, and then you want a 0 here. So what you need to do is subtract this first one 2 times. So this will become 0, obviously. And then you get -1 minus 2 times 0. Let me write here what. So this is row 2 minus 2 times row 1. Okay, then here you get -1, and then 3 minus 2 is 1, and then 5 minus 6 is minus 2. Yeah?
Are we allowed to use calculator?
I'm pretty sure you're not. No.
Sorry.
Okay, so this one needs to become 0 as well. And you kind of always use the pivot row for that, right? So you could subtract 1/2 of this row, but it's better to just use the first one and do row 3 minus row 1. So this will be R3 minus R1. So you get 0 here, then 1 minus 0, and 2 minus 1, then 0 minus 1, and 4 minus 3. And this one's already 0, so let's just keep that. Okay. What's next? Any suggestions? The next column, yeah. So we need a 1 here and zeros below it. Okay, so to make this a 1, you could either swap these two, or you could multiply this row by -1. Okay, so we're keeping this one again. And then let's do this one times -1. So it's 1, 1, minus 1, 1. Right, and then to get a 0 here, we need to add this one once, yes?
If we multiply the second row
with 2 and then we add it to the fourth one. That makes all zeros, right?
Yes,
Yeah?
but you want to make a 1 here,
You want,
not a 0.
yeah.
Right, so for this one we want to make a 0, so we add this one once, so this will be R3 plus R2. And then you get 0, 0, 0, 0. Right, if you add these together, you get a row of all zeros. And same for this one, you need to add 2 times row 2, so this will be row 4 plus 2 times row 2. And again, this will be all zeros. Right, because these 3 rows are just multiples of each other. Okay, anything else?
What did you do in the last row?
So you want to make a 0 in this place as well. So you need to add 2 times this row.
Okay.
And then it turns out all of these will become 0. So is this done? Is this row reduced echelon form? Yes? Okay, so you have 2 pivots here. And then this is all 0, so this is done. Okay, and the rank of A, yeah, why is it 2?
2 pivots.
Yes. Okay, so the rank of A is equal to the number of pivots. Okay, so to find the rank of any matrix, all you need to do is row reduce and count the pivots. Okay, next question. Question B is determine the dimension of the null space of A. So let's start at the end. Is it clear what the null space of A means? So the word space kind of suggests that it should be a subspace of something.
Is the space of 3 variables A?
Yes, kind of.
What does it do?
Hmm?
What was it? No space.
So if you want to multiply A by a vector, it should have 5 entries, right? Because for each column you need 1 element in the vector. So A maps from R5 to R3. And the null space is the part of R5 that gets mapped to 0. So it's all vectors that if you do A times X, then you get all zeros. Oh yeah, 4. Okay, yeah, 4 rows. So what you could do is look at this again and just determine from this what gets mapped to 0. Because if A times X is 0, then the reduced form of A times X is also 0. Okay, that's for the same X exactly. So you can use this one instead of A. Right, so you could see from this that these 3 variables are free. So you're going to get 3 vectors in the basis of the null space. Let's just do that for an example, and then at the end I will show you the easier way. So from these things you can make three vectors. So is it clear to everyone that these three are free? Because they don't have a pivot, and these two are not free, right? So we can make one with x3, one with x4, and one with x5. Okay, and then these two rows that have a pivot tell you what the last two numbers should be. So this row means 1 times x1 plus 0 times x2 plus 1 times x4 plus 1 times x3, sorry, and x4 plus 3 times x5 is 0.
But then you need 5 vectors there, right? Instead of 3?
No. You get 1 for every free variable. Okay, so in order to be in a null space, you must have that this times x is all zeros.
Yeah, in total it's 5 vectors, but for free variables it's 3.
So what you get here, so this, let's start with x2. So this says that 1 times x2 plus x3 minus x4 plus x5 is 0. Okay, so x2 is minus x3 plus x4 minus x5. And you can add that to each of these. So if x3 is 1, then x2 must be minus 1. If you have 0, 1, 0, then you get x2 minus 1 is 0. So this should be plus 1, and here you get minus 1. And the same for the first row. So this was a 1 here as well. And then 1 again. And then here you have 3, so you get minus. Okay, so if you want the basis for the null space, you look at the reduced form. You get 1 vector for each free variable, and then you use the non-zero rows to fill in the rest.
How did you decide the row 2, like this one left, so it's x2?
That's what it says here.
Okay, so because we have 0, that's why you neglect x1.
Yes. Okay, so what's also fine is if you just say the rank of A is 2. We know that from part A. And so it's always the case that the rank of A plus the dimension of the null space is equal to the number of columns. Right? Because each column either has 1 pivot or it doesn't have a pivot, and then it gives you 1 vector in any basis for the null space. So because A has 5 columns, and the rank of A is 2, you can immediately say that the dimension of the null space is 3.
Right, so
Yeah.
the answer for B is 3.
Yes.
So just 3, and those 3 vectors is the answer for C,
This is C.
correct?
Yes.
Oh, okay, yeah. Yeah, that's all.
Can I ask another question?
Yeah.
How did you calculate the first? Can you write the formula for the first choices? For the first row. So it would be x1.
x2 plus x.
No,
plus
x3. X3 plus x4 plus 3 x5.
Yeah, so
For the
you
first
get, so from the first row, right, let's put the other ones at on the other side immediately. So x1 is minus x3 minus x4 minus 3 x5. Any questions about A? About 1?
Just to make sure, the question B asks you for an integer, or a number to
Yes.
this. Okay, since you did B and C at the same time, so I got confused. But B just needs number
okay,
3,
yeah.
and C requires those 3 factors. Okay.
Yeah, so maybe to be correct, you can say this. Okay, so for question 2, you get a linear function from R4 to R3. I'm not going to write the whole thing down. So the first part is to determine the standard matrix corresponding to it, which just means to write it in a matrix. So you get 1, 2, 5, 2, 3.
Oh, that's it.
Okay, that's all. So the question is determine the standard matrix corresponding to the function t. And that just means to write in a matrix the coefficient. Okay? Easy points.
Yes. Yes. Yes.
Then part B is t a one-to-one function? So one-to-one means that everything that gets mapped to is only by one original. Right? So one original goes to one point in the image. So for example, if your matrix is all zeros, then you map everything to 0, so then clearly it's not one-to-one, because more than one thing goes to 0. So any ideas how we can check if a matrix is one-to-one or not?
Do I have to reduce it? And then check if it's like linear independent?
Yeah, maybe. Check if what is independent?
Each column?
Right, yes. So it's true that a matrix is one-to-one if and only if the columns are all linearly independent. Right? Because if they are not independent, then if you reduce it, you will get a row of all zeros, and then clearly multiple things get mapped to 0. So in this case, there's 4 columns of length 3. So are they independent?
No.
No. Is that clear for everyone? So if you have vectors of length 3, you can have at most 3 of them that are linearly independent. Right, so another way to think about this is this matrix maps from R4 to R3. So because 4 is more than 3, you cannot avoid that you map multiple points to the same one in R3. Yes?
Do we have to state like in R4 and R3, or can I write down there are more columns than rows?
That's fine. Either one is fine.
Yes.
Okay, so this is kind of an easy case where you have more columns than rows. But what if, for example, you didn't have this fourth one?
So you could check if one column is a multiple of the other.
Right? So, but if it's three of them, or maybe even more, then it can be kind of hard to see if they are multiples or not.
Check for pivots.
Hmm?
If they all have a pivot.
Yes, exactly.
Just reduce it.
They're reduced.
Yeah, so just reduce it again. Right, it's kind of always the same first step, yeah?
And what if you reduce it and you don't get 3 pivots but only 2? It's still independent then?
No, so it's independent if and only if every column has a pivot. Right, yeah?
If it is not one-to-one, it's onto, or it's not the case?
No,
Okay.
it could be either. So, and what if you have only two columns? Could it be one-to-one?
No. Because we have 3 vectors with 2 columns, so there will be at least 1 and 3.
No, because 2 columns implies there's only 2.
If you have something like this,
Columns 2 vectors, yeah.
right? It's the same as when you have 3 columns. When they all, if all the columns have a pivot, then it's one-to-one. Okay, then part C is to check if it is onto. So is it clear what that means?
Didn't he mention something about skipping 2C because we haven't discussed?
3B and 3C.
Okay,
Yeah,
so
we're skipping 3, B, and C, and 4.
okay.
Wait, why?
I forgot what onto
We don't get those questions?
because we haven't discussed those.
Where it says skip, I'm in on the course.
I think it's because it's like in the end of chapter 6 or
Okay, so onto means we agree that this maps from R4 to R3, right? You start with a vector with 4 entries, and then if you multiply it by A, you get something with 3 entries. So R4 to R3. And onto means that everything gets mapped to. Okay, so everything in R3 should have some original in R4 that maps to it. So for example, if the matrix was all zeros, then is it onto?
No.
Yes, no? So if you have all zeros, then regardless what you put in, you get the 0 factor, right? So there clearly are things in R3 that don't have any original. So the question is if you can reach anything with this. So onto right? So for every b in R3, you need some kind of x, so that a times x is precisely b. Okay, and if you do a times x, if you look at what happens when you multiply stuff, then anything of the form a times x is just a linear combination of columns of a. Right, so for example, if I multiply this by 1, 1, 0, 0, then the result is 1 times this column plus 1 times this column. Right? So if you think about what it means to multiply this, you get, for the first one, you get 1 times this, and then plus 1 times this, and these go times 0. So what you get is exactly 6, then, right, 1 times this plus 1 times this. Okay, so everything that you can possibly reach is all the linear combinations of columns of A. So the question is, do these columns span all of R3? Okay, and how can we find that out? I'll give you one guess for the first step.
So
Yeah.
what was that example that you just removed, that 1, 1, 0, 0? Where did that come from?
So the point is that if you do A times X with any vector X, then the result is a linear combination of the columns of A. So for example, if X is 1, 1, 0, 0, then the result is 1 times this first column plus 1 times this second column. Okay, so for any X, you always get some kind of linear combination of these columns of A. Right, so the only options for this B are precisely the linear combinations of the columns. So let's reduce this. Okay, so step 1 is to make zeros here again. So this is minus 2 times the first row. So to get a 1 here, you can multiply by minus 1/2. So this will be 3 over 2. 3 over 2. And then for this one, you need to add 4 times the second row to get to 0. So you get 12 plus 4 times minus 3. And then 13 plus 4 times minus 3. Okay, so there's pivots here, here, and here. What does that mean? Is it important that the pivot is here instead of here?
So x3 is a free variable.
Yes? So the question is, what is the span of these vectors, of these columns? Is there 3 of them that are linearly independent?
Yes,
Yes, why?
because there are 3 pivots.
Right. Okay, so there's 3 pivots. Every row has a pivot.
Okay.
So the span of this is 3-dimensional, so it must be all of R3.
But we know that right now that a 4-dimensional matrix maps onto a 3rd-dimensional matrix. But where
We have only one matrix. We know that A maps from R4 to R3, and that it maps onto.
So it should be stated beforehand to which dimension it maps onto.
I mean, it's clear from the number of rows that it maps to R3.
Okay. So because it goes into from dimension 4 to 3, we can say it's onto.
No, it doesn't have to be.
So it
Right?
can
Because
be
you
a
could have
different,
all zeros and then it's not onto.
but it could be a different dimension as well. Like for example, from the 6th to the 5th dimension.
Yes? But that's, so if it maps, for example, from 3 to 4, then it's never going to be onto. Right? Because you can only reach 3 dimensions.
But so in the question, the dimension needs to be stated, which you're trying to reach, basically.
No, because you can tell it from just from the number of rows of the matrix. Okay, so for 3, we're only going to do part A.
We did in the lecture. That's
So you get 3 vectors. And the question is if they are linearly independent. So I think in the case of 3 of them, it's already kind of hard to just try if you can make some kind of linear combination that ends up on all zeros. Right, so maybe if you have 2 of them that are length 2, then you can just see if they are or not, but in most cases it's better to have some kind of procedure that will always work. So how are we going to do that? Yes, right? So let's just squish it together. So now the question is, are the columns linearly independent or not? So what shall we do?
Reduce.
Yes.
I was just going to say, well, you know, if you only have the trivial solution for zeros.
Yes, right. So the columns are linearly independent if and only if this times x is 0 has only the trivial solution. Right, and so to check that, we row reduce this. So we need zeros here again, so let's add 2 times row 1, so get 2 plus 0 and 0 plus 2. And this one needs minus 4 times the first row. So that's 1 minus 4 times 0, and then 5 minus 4. And then this one is fine already. Right, we need a 1 here. So